Sir, shall I initiate recording by 6:33, sir? Now it's 6:32.
Another 2 minutes wait, madam.
Yes, sir. Yes, sir.
Good. Akila,
Yes, ma'am.
Venugopal sir AI ஓடது வந்திருக்கு பாருங்க, note taker.
I'm not admitted. Okay, okay.
அவர் சொன்னாலும் ஏன் அப்படியே அவர் பண்றாரு தெரியல.
இல்ல சார், ஏதாவது when they are just exploring something they will try to admit. அது முதல்லயே பண்ணிருப்பாங்க. Whenever they go in with their email ID, the note taker will also be there.
அப்போ இது பண்ணுங்க, ஸ்டாப் பண்ணுங்க.
Disable பண்ணு.
Removed, ma'am.
Okay, okay, yeah.
Yeah, okay, we can start now.
Okay, sir.
Mm.
Good evening to one and all present here who have joined. I welcome our today's speaker, Dr. Rajiv Chopra, sir, for this webinar on quantum software development lifecycle. Now I request Mr. H.R. Mohan, sir, Chair Events IEEE, to welcome the gathering and also to provide the introduction about the speaker.
Greetings and good evening to one and all. On behalf of the organizing units, IEEE Computer Society, CSI, and ACM Chennai, let me extend a warm welcome to our today's speaker, Dr. Rajiv Chopra, members and my colleague from the organizing units, and the participants joined the Google Meet through the link and those watching the session through YouTube streaming. We are starting our new year, 2025, with a relatively new topic, software development lifecycle for quantum computing. The question of how software development process is different for quantum computing when compared to classical computers was lingering in my mind for quite some time since the quantum computing started gaining attention. Today, we are going to get some insights through our webinar presentation on quantum software development lifecycle by Dr. Rajiv Chopra under the Author Speaks series of webinars. Over the period of time, while the software research has moved from software development lifecycle to web software development lifecycle and now to quantum software development lifecycle. About 2 years back, we had the presentation on web software development by the same speaker, Dr. Rajiv Chopra. In today's presentation, focusing on software development for quantum computing, Dr. Rajiv, apart from briefing basic quantum computing and programming, will attempt to provide answers to a few questions such as, what is quantum software engineering? Can we use the same techniques of software development lifecycle and web software development lifecycle for quantum software development lifecycle? How the quantum programming languages differ? Are there any open source IDE? Can we reuse the code? Or one human computers will still useful in quantum computing? Will there be a quantum laptop? Such as these questions will be highlighted in today's presentation. The presentation is based on his recently launched book, Quantum Computing Techniques, Theory and Practice. Now let me formally introduce the speaker, Dr. Rajiv Chopra. As stated earlier, Dr. Rajiv is not new to us. He had delivered a presentation on web software development during the peak COVID time, while his family members were suffering from COVID attacks. Dr. Rajiv Chopra, Associate Professor till 2024, now a full-fledged professor, is a prolific author of 42 books. He has several referred and peer-reviewed research papers in international and national conferences and journals to his credit. He has participated and addressed in about 50 seminars, workshops, symposiums, webinars, and conferences. He is a reviewer and editorial board member of several journals and conferences also. Dr. Rajiv is a life member of CSI, ISTE, and Center for Education Growth and Research, that is abbreviated as CEGR, an independent and non-profit education think tank. He is a certified ethical hacker, Azure Cloud certified, CEGR certified researcher, and certified data engineer, certified in Java and Python assessment. Dr. Rajiv has 7 awards to his credit, which include Academic Excellence Award for Best College Teacher of the Year from International Association of Research and Development Organization in 2019, Best Researcher Award in New Science Inventions in 2020, Lifetime Achievement Award from USA Book of World Record in 2024, prolific author of CSE and AI Data Science from London Book of World Record in 2024, Rabindra Ratna Puraskar Award for Literature in 2024, and an award from American Merit Council in 2024. I am pleased to announce that in the new year, Dr. Rajiv Chopra starts his teaching journey as professor of CSC at Dronacharya College of Engineering, as against our announcement as associate professor of CSC at Guru Tegh Bahadur Singh Institute of Technology. Our hearty congratulations to Dr. Rajiv. With this introductory note, let me welcome Dr. Rajiv to enlighten our participants on quantum software development lifecycle. Over to Dr. Rajiv, please.
Okay, good evening to all. Thank you, sir. I will just share my PPTs, I think. Is it visible, sir?
I think
Sir, the presentation is not appearing, sir.
Your laptop screen is seen, but presentation not there.
Okay, just a minute, I will check. will share again.
Let it be, ma'am. One small issue, I think.
So presentation, select the window.
Yeah, I've selected the window.
Yeah, selected the window and go to the presentation screen, not the PowerPoint screen. So you will be in the presentation. First is presentation mode. Just use it, put it in the presentation, then use the Alt tab to go to your Google Meet window and go for sharing. Alt tab.
No, Alt tab I'm using, but
So select the Google Meet and then share.
no, once I go to presentation mode, it is just in presentation mode. No, how
Yeah,
can I
that's
just
what. That's what. You cannot have any other control. So have the control button, Alt tab, both together. Then it will shift from the presentation to the Google Meet. You can select. Okay, have you selected, sir?
now is
Google
it
Meet.
okay?
Yeah, then you can go for normal sharing. Share. Up arrow. Down, no, sir. Up arrow. Normal presentation sharing. Sharing your screen. In the Google Meet. Down. Up arrow. Otherwise, can you just send your PowerPoint
Yeah,
to?
it is there. Akila has shared it with Akila. Presentation. PPT is there. Akila.
Sir, WhatsApp, you can just share the PowerPoint to Akila.
Yeah, it is being shared to Akila.
Okay.
It has been sent. Yeah.
Okay. Okay. Yeah, it's coming, sir.
Yeah.
Yeah. She has. Yeah, coming. Sir, instead of yours, she will be controlling that, and you can just keep talking, sir.
Okay. So I
Yeah,
have to
that would be
close. Okay.
No, you can continue presentation, but you can inform Akila to just move the slide or something like that.
Okay. So I thought of showing the book and the book cover for my new book on quantum computing.
No, you can still show the book cover. You are visible in a separate unit. You can show the book now.
Yeah, you can open. You can just raise your book and show it in your camera. If you have your physical book with you, you can just show it to us.
No, it's not coming to that
Moving.
mode, tab.
No, you just
No,
show
sir.
your book now, sir. You are show your book. You take it in your hand and show.
Physically, you have it, no, sir. Book with you, right?
Yes.
Then
Yeah,
that
just
is
show
you
it.
just show it to the camera, sir.
Put it on your face, sir. Front side of your face.
Yeah, just
That's it, sir.
That's
Okay.
Yeah.
good. So the book,
Good, sir.
yeah, this book has been released recently, and I think we can now start with the technical part. So just a minute, I will.
Dr. Akila will be moving your screen. Yours is not coming.
Okay.
Yeah, you just stop presenting, sir.
Achha, I have to stop presenting.
Yeah. Akila is presenting your slides, and you can just keep talking about it, and you can just give her control. I mean, saying that to move the slide. She will be moving the slide.
Yeah, now I think I have stopped sharing.
Yeah,
So I
yeah.
will just start with it.
Akila ma'am, can you just present it now?
Can we move to the next page, ma'am?
Akila, are you there? Yeah. It is coming.
Just move next slide, ma'am.
Basics
okay.
of quantum computing.
Yeah.
Okay. Can I start?
Yes, sir.
Yes. Okay. So, on the left side of the figure, I have shown how we used to work on classical systems, when human machines, either it was logic 0 or logic 1. But when I'm talking about the qubit, the basis states are same, 0 and 1, but all of the states in between are in state of superpositions. Now, this is similar to, the coin problem. Suppose I am tossing a coin. When I toss a coin, when the coin is in my hand, um, either it is head or tail. Then I flip the coin, it goes to the top. Again, it is in some head or tail position. But what is happening in between? What is the state in between? We are not aware of. So such a state is actually the state of superposition, where the bit is in both 0 and 1 position at the same time. Such a bit is actually called as a qubit. And the state of this qubit is represented by psi as a vector from origin to the point on the block sphere. A qubit can be in the basis state, 0 or 1, or in a superposition state. So if I represent what is psi is the qubit which I have shown in dots as superposition on this block sphere. So why the basis states, the north and the south pole, they are 0 and 1 only? Because the situation is analogous to the coin tossing. When the coin is at the top, either it is in 0 and 1 position. When it is in my hands, it is in other 0 and 1 position. So those states are known. But in between, if we try to find out the states of this qubit, these measurements collapse to classical only, either 0 or 1. So it is not possible to measure that much easily, and there are some challenges that we'll be seeing when we are trying to measure. So this superposition state of this, four dots, for example, I've seen on this block sphere, can be represented as psi in cat notation given by Dirac, and that is equals to actually alpha naught into 0 state plus alpha bar into 1 qubit state, where the absolute value of alpha naught square plus alpha 1 square is 1. So the instead of going more detail into it, because that needs a separate lecture, what is this? I just wanted to represent how do you represent a qubit. Here psi is a qubit. So if you see a 4-bit classical register, if we take a traditional register and it is a 4-bit classical register, then it can store one number from 0 to 15 at a time. Whereas at the same time, if I have 4-qubit register, it can store all the 16 numbers in the superposition state. So the best solution out of it is found, and then the circuit responds to that thing. So this will become clear when I go to the next slide. Ma'am, next slide, please. There are 3 pillars of quantum computing on which the quantum computing rests: superposition, entanglement, and interference.
Dr. Akila?
So, next slide.
Superposition, entanglement, and interference. So, like for example, before we take the example, so we say the superposition we have just seen that how whenever we have to understand quantum computing, we have to keep one thing in our mind, that the situation is analogous to flipping or tossing of a coin. So when you are tossing the coin, The top and the lower position we know, but what about the intermediate positions? Because the coin is in superposition state at that time. Then the second pillar on which it works is entanglement. Entanglement means, if I know the state of one qubit, I can find out the state of another qubit, how much far they are, that irrespective of that. So this entanglement, if entanglement is not there, then the qubits will not survive. Then interference, at the same time, interference is also there. That also, you know, uh, plays an important role in quantum computing, because because of this interference, which is either constructive or destructive, we can make out the final state. So we will see that slowly when we go to. If very interesting example I could see, like if suppose the this superposition state is psi, qubit is represented like this: hello plus high, and then tensor flow. We are doing tensor product with world psi. Now here this is nothing else but hello plus high tensor product with world. Now what this example shows is that the superposition of greetings like hello and hi are entangled with the world, with the word world. So observers would measure it to yield either hello world or hi world, depending on the context. So this is how these three, superposition and entanglement are working. And this is a very common example that we have. Hello and hi, they are there, and then the tensor product with world. So this will be hello plus I tensor product with world. We can write it like this. So it will be either the superposition of hello and hi entangled with the word with the world. So when you measure it, your output will be what? Hello world or hi world, depending on the context. So this is an example to show superposition and entanglement. So coming to the main topic now, the quantum software development life cycle. Now, initially when we were all students, we used to study software development life cycle. Then we came to web engineering part. We had software development life cycle. Today we talk of quantum software development life cycle. So before we see how this has to be done, let us define what is quantum software engineering, and then we will see the life cycle. Now, the art and science of being able to write such a software which is purely quantum in nature to be executed on a purely quantum device, that is software engineering, quantum software engineering. You have to write the software which is purely quantum in nature. Keeping in mind the superposition state psi, we have to write the programs now. What we have observed is that there is slow transition from John von Neumann computers based computation systems to quantum systems. This helps in better quantum software development. The need is now to conserve the basic principles in quantum software engineering also. So whatever we had in software engineering, in web software engineering, they have to be preserved and conserved for quantum software engineering also. I will show you with the help of other slides how this is being done. There are many future application areas like quantum AI, quantum machine learning, quantum deep learning. They will benefit from quantum software engineering. Quantum software engineering, it will focus on the ideas, the guidelines, and the procedures for setting up, advancing, and preserving applications based on quantum computing. All basic thing activities like generating ideas, maybe through the requirement elicitation techniques like fast and meeting, brainstorming, all those guidelines have to be framed, and the procedures have to be set up, so that quantum computing can be performed, quantum programs can be written, and we have to do mapping from the classical SDLC to quantum SDLC. Now many quantum programming languages are there, and some more are also being developed. So in-depth coverage of quantum software engineering and QSDLC, basically the focus is on software reuse methodology. So reuse is the keyword that we are using today. We're trying to reuse all the classical things and then trying to build up the quantum systems. So it is not that the classical systems will disappear. In fact, the classical systems and the quantum computers will work together. Even the supercomputers, they when I saw the first time, I read that supercomputers will be slower than these quantum computers. I was thinking, now what will happen to supercomputers? So much we have spent, so many we have developed, but the next day another research paper appears that the supercomputers and quantum computers, they can be used in conjunction also. And then all the tasks, however, which used to take several years earlier, now they can be done in few minutes. So we will see that. But naturally, there are some, ma'am, next slide. Challenges in quantum computing. Quantum computing challenges basically include environment challenges, maintenance challenges, comprehension challenges. When I'm saying environmental challenges, it is like software infrastructure, hardware infrastructure challenge, quality and documentation, quality and implementation. Now, with the thing is that when I'm talking software infrastructure, I have to, the challenge is integration, how interoperability can be obtained between the classical and these quantum computers in a hybrid approach. The execution itself is a challenge. The new framework is a challenge. Then hardware, new hardware are being developed every day. I will be focusing on few of them. They are being developed every day, and new experiments are being done. Tomorrow morning again you will find something new on Google or somewhere. So hardware and performance, they are also two challenges. Then the maintenance part, quality and documentation, and the comprehension, quality and implementation. We'll see some of these points one by one. The challenges are here. Environmental challenges, very vital role with respect to quantum behavior. It is further divided into two categories: software infrastructure, hardware infrastructure, as I told. So when I say software infrastructure, that refers to the framework that can be reused in the execution environment. Now, what is there is that the already available tools, many of the source codes, they are being reused for quantum computing purpose. So the framework which are already there, they can be modified, and they can be reused for quantum computers. This is so because the frameworks are mostly created for API protocols, and making changes to it is also a challenge for the developer. Furthermore, there is lack of standardization. The standardization is still in its infancy. Companies like NIST, IEEE, they have developed some standards, and slowly they are moving every day. In a day or so, they give a new standard for quantum. Secondly, integration, as I told you, is also a challenge. You have to integrate your quantum computers with other technologies like blockchain or AI. That also is a challenge. Execution also struggles here with the setup environments and the simulators for interaction between non-human computers and quantum systems. Since it's a hybrid structure, how will they communicate? How will they interact? Then hardware itself, we need more specialized tools are required, and every day new chips are coming, new hardware is coming. But the problem is that the inherent problem is that of noise. So people have started working on that quantum error correction and started giving new techniques for them so that this can be prevented. Performance is another constraint due to the limitation of the resources in this quantum system. But what is the greediness today? What we want? We want competition with lesser resource conflicts. And all these are naturally the challenges that we are facing. In addition to this, next slide, ma'am, comprehension, documentation, an essential part of QSDLC. Now you can go for, you can use a SRS document, but now you have to modify that document for quantum software. That is what it is saying, reuse. So document comprehensibility, document quality, these are also to be maintained in the document. Then comes the coding. Several IDs are there. They also, but there are some challenges. What I found was that working on QSKIT and debugging part was not that much easy. So different languages, they require different IDs also many times. That is a challenge for developers. They have to understand all these programming languages thoroughly. Then code quality. What we are doing is reusability and code understanding. These two things are to be done. and the code quality can be maintained. Like we need more efficient and debugging techniques, testability, readability. All this has
I
to be
think it is in
there.
the next slide, sir. Can you move to the next slide, please?
Okay, this one.
Akila? Akila?
I think now it has come to coding slide, sir.
Yeah.
Is it okay?
Yes, sir.
Okay. So the need is to formulate actually a layer that interfaces my quantum software architecture and quantum hardware architecture. That is also a challenge. We call this as QSA, QHA standard. And QHA is a blueprint on how a quantum device is organized, so that its components like CPU, quantum processing unit, work cohesively to perform tasks like quantum computation, quantum memory management, and IO management. So the hardware components have to be developed, and so that the interfacing can be done. So that also becomes a challenge. And QSA is a more abstract concept if you take software, because that gives a design and defines the components and relationships among them. Note that here that QSA is expected to enable quantum developers to enable high level of abstraction. So if I have quantum software architecture, so that provides a high level of abstraction to the developers also. Then there is a need of quantum operating systems also, that helps to manage quantum resources. So if we see diagrammatically, next slide ma'am, then see diagrammatically, this is how it is happening. You have a quantum hardware architecture, generalized one, quantum software architecture, you need a quantum operating system, then universal quantum compiler. I will tell you what it is in the next slide. Then programming languages are needed. These are all the inputs to quantum software development lifecycle. So the programming language has to be now the quantum programming languages. So control, if we see in this diagram, control is also a layer in between this QSA and QHA that performs the translation of quantum operations, like the gate application into analog signals. Then Universal Quantum Compiler does the following translation. With the help of this chart, we can see higher level language quantum programs. They are converted with the help of Universal Quantum Compiler to control level maps, then hardware level pulses, then that will manipulate the qubits. So QSDLC also involves its inspiration from classical QSE to create reliable, scalable, robust, efficient, and maintainable software, which is same as we used to have earlier. Even developers of quantum hardware, they are facing some challenges like scalability, error correction, decoherence, temperature requirement, system integration. Decoherence, that is inability of the qubit to remain in the state of superposition due to environmental effects like noise and all those things. So a qubit tries to lose its state. So decoherence and all these are the challenges that we have to take care of. IEEE standard, next slide. IEEE standard association and other challenges are also there. There is lack of standardization in quantum field. IEEE Standard Association (ISA) gives some standards for quantum computing, quantum communication, and sensing. Some of these standards are like US NIST's post-quantum standard given on 13th August 2024. They gave first three cryptographic standards like MLKEM, MLDSA, SLHDSA. Then IEEE 2995 standard for trial use, standard for quantum algorithm design and development. IEEE 1913 standard, software defined quantum communication. IEEE 1943 is standard for post quantum network security. So every day today also NIST has given some new standard that we will see in few days. And then integration challenges are there, as we have already told. Execution also struggles with the setup environments and simulators between these Venn Newman architectures and the quantum systems. So there are hardware infrastructure challenges, there are performance challenges like limitation of resources and the greediness of computation for resources. So there are some comprehension challenges also faced by the developer, like documentation challenges. Documentation should be comprehensive, understandable. Coding challenges, inadequate IDs and compilers. Coding quality challenges, debugging, testability, and readability. So better testing techniques are required to test the quantum software now. So now what is actually happening is that SDLC phases, they are being, reused now. The SDLC phases are being induced and reused now. Instead of SRS, software requirement specification, now we say QSRS, QSD, quantum software design, quantum software implementation, quantum software testing, quantum software maintenance, and quantum software reuse. So reusing can be done at different levels. That also we will see. So if you see quantum software testing, we are talking of bug types. We have to identify the patterns. We have to identify. Then there are benchmarks also. We have to bugs benchmarks are also given by some of the tools, like uh, benchmark tools are also to be given. Some tools like QBugs, Bugs for Q, they give some bugs benchmarks also. So let us see the companies like D-Wave, Google, Honeywell, IBM, and then they are promoting their developed quantum software kits also and their programming languages also. D-Wave uses QMASM as a programming language and it uses Ocean tool. Google uses Circ and TensorFlow to develop quantum applications. Honeywell uses trap-down technology providing dynamic qubits which rearranges for better quantum algorithms. IBM provides quantum computing as a service. Qiskit is the quantum programming language used by IBM. Also, it supports other libraries like Qiskit Terra for servicing. Then Xanadu, it uses Pennyline and its full stack of libraries to develop quantum programming. It trains quantum computers very similar to the neural networks. Next. So quantum software development life cycle, we have requirement analysis phase, design, implementation. This we have already told. So just life cycle when we talk of, this is the life cycle and better insights are needed. So if we if compare and integrate traditional software engineering versus quantum software engineering in this next slide. So if you see the VMC model on the left hand side, John von Neumann's stored program concept model. Here if you see what we do requirement analysis, then designing, then implementation, coding, that is, then testing, and then maintenance. Same thing is been done in quantum software on the right hand side. But now your perspective, your view will be in terms of quantum requirements, quantum circuits, quantum architecture, quantum deployment, quantum software testing naturally, and quantum software reuse. So when I'm reusing, I can use quantum software, I can use qubit also, I can reuse, I can use quantum circuits also, quantum state can also be reused. So this is the comparison and some phases explanation also I have given, like you have quantum hardware requirement specification, software requirement specification, you can develop QSRS document. uh, the focus should be on, like the quantum tools, quantum integrator plugins, logical quantum circuit synthesizer, even classical SRS. Then quantum hardware requirements have to be there. It can include the metrics like number of qubits, error rates, qubit connectivity. Together they are called as quantum volume. So they are we call this quantum volume. All these are also to be taken in as far as hardware are concerned, and you can write this in hardware requirement specification document. Then design is also there. Better hardware design approaches, quantum software design approaches are there, and we have to find out the relationship among the modules, the cohesion and coupling between these quantum modules, the data structures needed for the next stage of implementation. So all those things can be there because the design has to be very good, otherwise your quantum project will also fail. Then architectural design, the functions and the relationships among quantum hardware, quantum detailed design, processing logic and data. These things will be focused in them. Then implementation, several open source software toolkits are there, like Qiskit is open source by IBM, Circ by Google, Pennyline by Xanadu, MSQDK, and then Intel Quantum Simulator, TensorFlow Quantum, Opsolve by D-Wave. Proprietary QSDK kits include D-Wave, Ocean, Rigetti, Forest, Icons, so many are there. Icons Quantum Cloud. Then testing is also there. That is the process of executing the quantum program with the intent of finding the faults. And this is to ensure that quantum software is correct, reliable, and performs well. So next slide, I show that when I'm doing testing analysis, I have to do robustness analysis, entanglement analysis, coverage criteria. So how the testing analysis is changing slowly. You can see we are mapping that the coverage criteria is now given by the total gates used in the circuit minus the gates infeasible. Then another researcher, Kumar, and his team, they have given description of mutation testing. where they have developed a tool Miskit that is to ensure again the quality of software, because the quality of the software will depend on how efficient your testing is. Then deployment has to be done. You have to perform again the same tasks for where it has to be deployed. Maintenance is there. If maintenance has to be there, you have to test this again. So you may go for quantum regression testing, because scalability, maintainability, reusability, performance and security, that we have to maintain. Quantum software reuse, defining crucial quantum qubit circuits that can be implemented for different quantum software. Now, what all things can be reused in this next slide? You can means, what do you mean by quantum software reuse? That means reuse of quantum state, reuse of quantum circuit, and quantum pattern reuse. It is suggested now to maintain a quantum pattern repository also. Many, the programming languages like Qiskit, when you compile the program, and if suppose there is an error, you will find the class of the repository of quantum pattern is there, error is there, and then that appears there. Then quantum reuse compilation, quantum state reuse, quantum software matrix, that is assessing the size and structure of quantum software. So all these things can be done here also. Hybrid quantum applications may have many quantum algorithm implementations, like clustering may be performed first, then classify may be trained using cluster finding. So this will further help in quantum machine learning and all those things. So clustering may be performed, then classify may be trained using cluster finding. So you may have many quantum algorithm implementations like this, as because it is hybrid one. So quickly, I will just go through the table: functional requirements and non-functional requirements. Quantum SRA. Now, when I'm talking of functional requirements of quantum software, I have to focus on defining the quantum features. Emphasis is on user quantum requirements, figuring quantum mechanism in the use case, authentication and security level. But non-functional requirements include defining quantum properties, emphasis on user expectations with quantum, figuring quantum as quality attribute, usability, reliability, scalability, and performance. So the quantum software engineering, it paces with those recent trends that is concerning the high level quantum based software architecture desired. The classical approach of software engineering can be induced and reused for this. That is the key, that you can induce and reuse the same approaches for QSDLC also. Then similarly for design, if you see, there are quantum design levels. It can be high level design like quantum abstract particulars, develop quantum modules, describing the functionality of each module, understanding of quantum gates. Low level design means coming back to the quantum data structures, quantum circuit and algorithm design, quantum interface design, modules communication. So these designs again, even the cohesion and coupling that we had earlier in software engineering, here also you have to find out the cohesion and coupling between the quantum modules. This can be done. So just you have to modify, you have to slightly modify the previous the SRS and all those techniques that were there. Why can't we go for brainstorming? We can go, but the point is that now the focus will be on quantum solutions and how the quantum problems can be solved. So the low level design will basically come to the data structure design, circuit and algorithm design, interface design, modules communication. So I mentioned something next slide. I'm telling you what are the patterns like. There are different patterns that can be obtained. The example of this can be, good example out of this can be uh, for patterns. You can maintain a repository for these patterns, like designing entanglement, creating an entangled state, and then these are the patterns in quantum algorithm designs. Then you can even go to quantum classic state, systematic superposition, creating equally weighted superposition of all the possible states, state preparations, initializing the input of quantum register. So the patterns that are needed for quantum software and algorithm design are given in this table. So these patterns have to be identified. And some of the proposed methodologies include like quantum universal modeling, internal the nature of quantum computing, internal implementation, and information handling. These are the foundations of QUML. So universal modeling language that we have, that can be used, the universal that unified modeling language that we had earlier, like rational rows, that can be modified to draw diagrams for this also. There are some general model languages, also generalized ones, like domain specific languages. Quantum based modeling languages are there. So then quantum modeling tools are also there, like Petrinets, Temporalogics, Quantum 4BPN, and SysML also exist. Several quantum programming languages like Quipper, Quasm, OpenQuasm, then Qiskit, QSharp, Circ, Project Q, so on. There is a long list of that. So when I'm talking of the test plans, as we do there in software testing, here also in quantum software testing, we can design some test plans. They can be test case descriptions, test design descriptions, test case description, test reports and logs can be made. Qubits measurements can also be done. Bug patterns and types, you have to identify, like for example, I was telling that there are two things needed to be observed, and then the patterns can of these bugs, they can be stored in a repository, and then just the Qiskit software, when you are running, if there is an error, it will take it that from that repository and show you the error. What are the different patterns that are observed bug categories here? Like for example, incorrect quantum initial values, inaccurate operations and transformations, inaccurate composition of operations using iteration, recursion, and mirroring, incorrect classical input parameters, incorrect deallocation of qubits, various bug patterns. In languages, as telling you, I told you that in Qiskit have been found various bug patterns and categorized. This helps programmers to uncover flaws more quickly and to spend less money on software maintenance. So giving incorrect quantum initial values can to the circuit itself can give you wrong results. So all these things, patterns you have to identify, and then these are the different bug types and their solving techniques. Suppose you have given false in quantum initial values. What you can do, assertion checks for classical and superposition conditions can be done. Then flawed operations and transformations, assertion checks for unit testing. So the bug types have been identified, and then their solving techniques are also being given. So we can't discuss this in detail now because the time is limited, but something I've told on QBugs, that is also a database of reproducible flaws in quantum algorithm. So repository is there, and then QBugs, it offers some preliminary suggestions also, developing a benchmark as test scenarios for simulating the glitchy behavior of this quantum circuit. Bugs 4Q, that is also there. Wang and Martoniso assertion-based methodology expands scaffold, a currently used quantum programming language. So they have used the expand scaffold, that is the quantum programming language. Wang and his team have used that. So with the aid of these, programmers may determine what is there if the quantum program states correspond to its predicted value in a classical superposition or entangled kind of state. This is to be determined. Based on this, potential claims in quantum software were divided into three categories: classical assertion, superposition assertion, and entanglement assertion. Now, what is the drawback of this is that each measurement made while debugging requires stopping of the program. So we then come to the maintenance phase. Maintenance accounts for 60 to 80% of the total cost of the software. That is very important, and even the quantum softwares have to be maintained. You have to alter the software programs because you have to maintain that. If they are not fixed before their release, then the customer will fix for you. Current research are concerned, re-engineering current conventional software system to interface new quantum. So the objective is to re-engineer the current conventional software system to interface with the new quantum algorithms. Redocumentation, reverse engineering, forward engineering again may be used here to alter the intended software system. To address these issues by migrating of quantum computing and existing cohabitation of classical and quantum, re-engineering must be explored. So quantum software re-engineering is also possible. That can also be done. Inserting quantum software components like patching is yet another challenge in this engineering, like plugins and all those things. So whether they are increasing the security or not, decreasing the security, that is still an open area of research. Model-driven re-engineering is another method of software modernization. So because IBM clearly focuses on model-based testing, model-based everything, they work on model-based. So model-driven re-engineering is also required. So when I'm talking of reuse quickly, again, we will just have a look on it. I've already told quantum circuit reuse can be done. So pattern repository can be there. Then, because if we already have, the useful collection of quantum circuits, we may systematically build effective quantum circuits by reusing and merging a collection of highly optimized quantum circuits. So quantum pattern repository, a specialized database used to store pattern documents and maintain linkages among them. So quantum circuit reuse can be done. Qubit reuse compilation can be done. Algorithms like quantum CNNs were implemented to preserve the total gates in the circuit, resulting in the increase of the circuit depths. Quantum state reuse, then quantum state can be reused. Another interesting concept here is plugin, as I told you, for using the quantum state. Quantum software metrics can also be done and should be done. Building hybrid quantum computer, the Van Neumann plus quantum coprocessor can be done, and this will do the task of data processing, error correction, and optimization. Whereas quantum coprocessor can do operations that are interactable by JVM machines model, like big factoring numbers, NP-hard problem, that is intractable there, but quantum coprocessor and these can work together. Some tasks can be given to Neumann model, some to quantum coprocessor. So if we see the QSDLC workflow, it is something like this. In classical software development, we have requirement analysis, observation, architecture, deployment, testing, implementation. But if I see in this right-hand side quantum circuit life cycle, quantum requirements are there, circuits are designed, architecture is created, and then deployment is done. So in this we can use quantum state reuse is also one of the inputs in this, and quantum software reuse is also the input. So classical quantum classical interface has been there. This shows the quantum workflow life cycle, and some things, some points have written on this. A challenge, some challenges are there. New languages are required for this, and some new IDs are required, because designing a new language actually is not a long-term solution. A comprehensive software engineering discipline is required for quantum software development. You have to manage numerous, software artifacts that are prepared for carrying out this operation. Exceptional quantum solutions will skyrocket in the next few years to come, and QSDLC is a live document that can be updated and expanded in response to new advances. So if you see the recent advances, that was we have heard of the Google chip, Willow. It uses 105 superconducting qubits, and it was able to solve the exponential problem, in 5 minutes, that even the supercomputer would take 10 raised to 25 years to compute. So, this thing has been done, and 10 raised to 25 years, they form 10 septillion years. So IBM is now also planning to get the same thing, and what they have done is they have integrated few chips together, like this one. This is the IBM Quantum Flamingo chip in this next slide, that can be connected together. They have done this experiment on two, chips of IBM, and then they will be extending it further in this year itself. So this is how the new hardware is coming now, and naturally with this there may be some changes in programming languages are also required. Then I thought of telling you, about some quantum simulators. One is QDIT simulator. It is a freeware developed by a daemon and can be downloaded from this homepage. Then you can use it. This simulator, it has easy to use graphics interface and with the drag and drop capabilities. So actually, QSKate and all those, they are programming languages. But this is a simulator that has easy drag and drop facility. And you can drag any circuit and put it on the form, and then onto the relevant point on the circuit. The transfer matrix can also be built. It can be designed to, can be used to design two circuits for check the circuit equivalence, ability to simulate not only gates, but higher dimensions also. And their facilities like, the erase gate tab is there. So you can erase a gate, then also you can add a bit, you can remove a bit. These tabs are available on this simulator. Then there is another simulator, CAD, for that is for called as quantum computer simulator, CAD for quantum computer, that is QCAD. This has been developed by Department of Applied Physics, School of Engineering, Tokyo. And then the source web link also have given. What are the key features of this QCAD? It is a total environment of quantum computing simulation, studying the quantum computations, graphical designing environment, simulators for several gates. Exportable files also are generated by this, and all the gates, they are there. They appear in the toolbar, QCAD toolbar. Just as you know, in MS Word we have a toolbar. Similarly, there is a toolbar, and QCAD toolbar. We can drag and drop, and when you start, initially there is a blank circuit appears. Various gates are pasted onto it. The circuits can even be saved with save tab. Simulations can be saved as text file .csv, comma separated values file. Major results can also be saved by save results. The design circuit can be saved as BMP bitmap file. So these are the this is another simulator, quantum simulator. So I was searching for what is actually the difference between a quantum simulator and an emulator. The main difference is that quantum simulator is used to study the behavior of quantum particles, while quantum emulator is used to replicate the behavior of quantum particles or complex systems in simulated environment. A quantum simulator is basically used to study the behavior of particles. So if you see quantum simulator, it is used to study the behavior of particles like electrons, protons, and neutrons, and it can be used to investigate the behavior of complex systems like molecules and materials that cannot be easily studied in lab. Then emulator is also there, then it is used to emulate. It is used to replicate the behavior of quantum particles or complex systems in simulated environment. So uh, you have emulators for your classical systems also. Similarly, the gate-based quantum emulators can be developed, and they many exist also. Some simulators I have told you these are there. So some steps which I performed during QSkit installation in this next slide. This is one of the experiments in my book. That first experiment, that what are the steps you follow in order to install QSkit. First of all, the operating system that you need is Windows 7 or later versions. Mac operating system 10.12.6 or later. Ubuntu, this can also be there. What are the prerequisites? Python 3.5 or later. Anaconda, a tool by Python for scientific computing. All these have to be installed. So for better and safer programming, we use Python virtual environments to cleanly separate QSkit from the applications. So I have installed Anaconda 3 on my system and QSkit in this, like for example, in this directory. So for this, what you have to do, open the terminal where you want to work and type the following command. Activate the environment, use conda command, and if it is Windows operating system, what are steps you have to follow? Install Anaconda, search for Anaconda prompt, open Anaconda prompt, use following. Now, it's not very difficult to download and install all these, because everything is available. You can directly go to Google and type that I want to install Anaconda, open free of cost. That also it can go do. Then you can. This is the command which I gave in my system, and I have to activate also this. So now you can install QSkit package that comes with various libraries like Terra, AER, Ignis, and Aqua. So you will say pip install QSkit. So you can verify your installations also, and then you can import QSkit in your programs, and then you may also get access to IBM Q systems when you go there. IBM Q gives users an exposure to several real quantum computers also. So it's called as IBM Q Experience QSkit. So these are some of the steps that we follow that I think will be shared. And then, the easiest of all, if you have to run a quantum program, you can go to Google Collaboratory. There directly you can run these programs, and you can type your program in Jupyter notebook, and then you can run the entire QSkit code. So it also has called what is called Google Colab. You can go to this link, and then you can use Colab. So everything can be run from here also. Jupyter Notebook, as we all know, it's an open source web-based application, and then you can write your program there. And then, but before that, you have to, install QSkit. Following those steps, and Jupyter Notebook you can use. So there are various methods that are used by QSkit itself by IBM, like quantum circuit method is there, then transpile is there, that transforms the quantum circuit into optimized version that can be executed on specific quantum device. Assemble module is also there, library is also there, Terra is there, Terra library, Aqua is there, Aqua Library, then AER is there, Ignis is there. You have to invoke all this with the commands. So the the installation steps, I think someone must be interested in, because you have to do this on your system. I've done on my system. Okay, so some references which I have wanted to share, like some of the papers, like in this uh, the paper, like a news this Piatini Peterson paper, Quantum Computing, a new software engineering golden age. This is also a good paper. Then, as far as testing is concerned, Ali SNUE, this paper is also very good. And then, the quantum development life cycle, Eric's paper by De Nivedita, is also a good paper. So I've referred to some of these papers. Then there is a book, Quantum Computing for Everyone by Chris, by MIT Press, that also I have referred. And the software engineering book by Bohem also I have referred. And naturally, my book also I have referred in the initial slides. And the second research paper was also good. So by Xav and all these things. So all these were the sources from where I've used them. So with this, I think I stop, because
Yes, sir.
So-
Dr. Kila, you can go for your Q&A. Shall we go to Q&A session, sir?
yeah.
Yes,
Dr.
sir.
Kila? Yeah.
Yeah. Thank you, sir. Thank you for your wonderful session. We have few questions given in the chat box. First, let me ask you those questions, sir.
Mhm.
So, the question from Sanjay Gupta, sir. Given a compute intensive application running in HPC cluster to
Mhm.
solve an optimization problem, if we want to
Mm.
leverage quantum computing to solve the same problem, how much percentage approximately of the entire SDLC time in development is needed to harness quantum power?
See, in as far as the speed is concerned, naturally, the speed of quantum computers is more. So basically, you want to know, ma'am, can you just repeat the question again?
Yes, sir. Given a compute intensive application running in
Mm.
HPC cluster to
Okay.
solve an optimization problem, if we want to leverage quantum computing to solve the same problem, how
Mhm.
much percentage approximately of the entire SDLC time is development is needed to
So each
harness
phase will take,
quantum
yeah,
power?
because now, because clustering is being done, so we may use machine learning algorithms, and then quantum machine learning algorithms may be used. So the time depends, actually. It can't be fixed, because
Yes,
earlier it was yeah.
yeah, I understand, sir. The time is fixed. What I am asking is that, let's say if I have taken 100 PD for development of this application, and now I want to port it on or align it with quantum capabilities, then how many additional PD effort would be required to re-engineer the same app or application using QSKIT or whatever, maybe 20 PD, 30 PD? That's what I just want to know.
Actually, I've not done that practically, truly speaking, but
Okay.
SDLC has its own time, because each will take its phase, will take its own time. Even if
Yes.
you are having hybrid approach,
Mhm.
naturally the time it will take its own time. The software
Okay.
development, project life cycle. That is what I
Mhm.
said. Silent maintenance is taking its own time. In fact, now the challenges are there, because it will not be
Yep.
that much easy. We
Yep.
can go with quantum machine learning algorithms for
Mhm.
such thing, and then you can solve that problem of clustering, and find out and compare your results with classical and quantum computers.
Okay. Thank you, sir. Thank you.
Thank you, sir. Next
Mm.
question. How to read, write superposition qubit values and how to read all three values 0, 1, 0 or 1 at the time in at a time in quantum computing.
Okay. See, actually, what has been found is that as we try to measure or read these qubit values, the superposition state collapses. It is not possible to measure. That is why we are going into that probabilistic measure psi. If you remember, then in quantum mechanics, you must have studied that thing. And it is not possible to measure. And there is a special theorem called as no cloning theorem. You cannot replicate the quantum state because in the beginning, I discussed about coin tossing problem. Suppose I have a coin in my hand, and I know either it is head or tail. When I flip it, it goes into the air. On the top again, I know whether it is head or tail. But what are its states in between? I don't know. If I try to measure these states, then the system collapses to this classical state only, either 0 or 1. That is the challenge that we are facing in these quantum computers. That is the thing. So you cannot measure how the value. If you take the topmost value, like for coin, or if you go to the top of the block sphere, it will be either 0 or 1. You can measure. Once you measure that, the system collapses to that 0, and then the process finishes. So if we have to measure the in between states 0 and 1, you have to use that ket notation psi, and based on probabilities you have to find out whether what will be the outcome, because data encoding schemes are being used by quantum programs also, quantum computers also. They use encoding schemes wherein each binary state is encoded into the quantum state. So if you use encoding like basis encoding, binary 0 is represented in ket as 0, 1 as 1. So it depends on which encoding you are using. Your company like D-Wave, they use density metric encoding. So based on that encoding you can do, but it is not reading all these three values together. Am
Thank you,
I
sir.
Sir,
clear? Yeah.
small doubt, sir. It's a fundamental doubt because in the conventional system, we know that 0 or 1 values are there, which is stored, and we can read and
Yes.
write. When in
Yeah.
the qubits, suppose I have 4 qubits, you said for 16 values are stored at a time. But the
Yes.
16
Yes.
values, we need to use it for process. In that case,
Okay.
when I read
Yeah.
0, when I read first time, I will get 0. When I read sometimes, I will get 4 ones, or whatever it may be. Still, that is a fundamental knowledge. I am not able to understand or conceptualize this concept. So, if you how these 16 values are stored at a time?
16 values are stored at the time, but it has to optimize that problem. This is advantage of this is that of our combinational exponential problems, like traveling salesman problem, or many problems which were intractable earlier, NP had hard problems, they can be solved because of this only. Because because all these 64 states are being stored at the same time, so it will naturally give one of the results. But if we try to measure that result, then the system collapses. But the thing is that all the 14 states it is storing at the same time. Like, sorry, the best way to explain this is, you imagine a coin. Now your question is that how can all these in between states when the coin was flipping be stored? This is at the same
Yes,
time.
yes, yes, yes. Correct, sir.
Yeah,
Correct.
so that is through this psi, the direct ket notation. We represent it. It will be the probability of half. Will be one will be probability of with the half, 1/√2. Other can be with 1/√2 or half probabilities. The total probability sum has to be 1. So we just imagine its probability that either it will be 0 or 1, 0 or 1, because coin is flipping. So all these 16 these intermediate states will be stored together, and then out of this the best optimized solution will be obtained. This is how we are getting optimized solutions for them, because on my laptop I have and I've given in my book also, my results also, I have implemented some many programs like this. And the thing is that the I could find that there are classes of errors, the bugs repositories there. They have made identified the patterns Qiskit has done, IBM have done, and then the thing is that in between states are all being stored. You can print those in between states. If we try to print, it will give you either 0 or 1.
Correct.
Because that moment you try to measure my Qiskit tool, it gave me something. I have tried for many programs, and about 11 questions are there in my book as experiment. So this is how all 16 states are being stored at the same time. This is what we want, because if this is there, I can solve my combinatorial problems where the solution is not there. Traveling salesman problem, many NP hard problems are there. So I get solutions to them because of this only.
One more question, sir. Thank you. This quantum computing, whether you want to use for specialized application or for all application in the digital computer, we can use it.
No, for all applications. Yesterday I was studying that it is useful for farmers, agriculture also, for healthcare also. Everywhere it is coming. Like we can, if it is healthcare, we can study the reports of the patients, and then the medical images, and then find out the better solutions. Farmer can use to optimize again the same.
My question is normal general arithmetic operations, matrix multiplication, inverse matrix.
Yes, we can use. Yeah,
use
one
it.
of the programs in my book is a matrix multiplication on quantum computer.
Okay.
You can do searching, you can do sorting, and in lesser time.
Okay.
That is the beauty of this quantum computer. The only problem is the fragility of qubits, the decoherence and noise. That is why in last few weeks what I've observed is most of the research papers they are appearing are on QEC, quantum error control. We have done that. Companies are saying that. And why they are doing this? This is one of the challenge. Noisy environments. The qubits are losing their coherence, and all these things are happening daily. They have lot of applications in every field, even matrix multiplication. Yeah, I have done in my book. I have given that program with the output, and I've run on Qiskit. So you can do any such program, searching, sorting, all these.
Okay. What is the time we can get a quantum laptop?
Quantum laptop. Very soon, this year. This year you will get quantum laptop. Yeah.
Thank you, sir. Thank you very much. Very nice explanation.
Next question, sir. Has translation has matured or still it is evolving, sir?
Transpilation. Yeah, everything is, quantum computers itself, they are in the infancy stage. It is changing day by day. And tomorrow, probably what we have today, tomorrow only you will get another translation method. Yes, it is maturing one by one every day.
Yes, sir. 1 minute, sir. There are few questions that has been asked at the time of registration, sir.
What?
Suddenly, 1 minute.
I'll present otherwise, Akila.
Yes.
Shall I present? Yeah, shall I present the questions?
Yeah, ma'am.
Yeah, okay. Sir, already you have given the quantum computing on healthcare. So can you just give a very brief note about it?
About
Sir?
what, ma'am? About
in
what?
healthcare.
Healthcare. Yeah. Quantum computing has already helped, the doctors or the developers to develop new drugs also by studying the complex molecular structures of these chemical compounds. You can analyze the images of the patients, and then they can be cured at a faster rate as compared to your normal method, and using classical approaches or classical computers. Quantum computers have given very fast solutions and better solutions
Precise also.
in healthcare. Yeah.
Thank you, sir. The next question is, instead of Python, any other language is good for quantum software development field? How it will run for future quantum software? How to tackle the version update?
Okay. Yes. because there are certain, there's one slide also in between you can share with them that I have told that penny lane. It is quite
Okay.
suitable when you're talking about quantum machine learning.
Yeah, yes.
QSKIT is the complete, documentation. If you go to IBM QSKIT site, IBM
Okay.
site, and you have to just enroll once with your login, and then everything you will get complete documentation. You can run your program. It automatically opens Jupyter Notebook. Just you have to click on arrow key for that to run, and then you can see everything. Complete documentation is there. What all new things are coming from IBM? They are also there. So. IBM source is the very vast source. You can see from there.
Next question, sir. Type of languages and algorithms required for software development and cloud technology to be deployed.
Uh, See, the you can, this is what I have been telling you. The classical algorithms you will be using, machine learning algorithms we are using, but now what we are viewing the solution is in terms of quantum. Earlier, we used to have principal component analysis that was there to reduce the data dimensionality. Today we talk of QPC, quantum principal component analysis. What is the quantum? What is the quanta? Quanta is actually the energy. E is equals to h nu. Planck's constant and all the that was there. We studied in school days also. E is equals to h nu. So that quanta is an energy actually, and that energy has to be utilized. And another beautiful property of this is that this quanta, when the electron returns back from its excited state, like it was shown in an hydrogen atom, it comes back to its ground state. So that time E is equals to h nu quanta is released. So that quanta we are talking about, we are utilizing that energy and
Okay.
trying to run these different applications.
Okay, sir. The next question is, how quantum computing provide more security?
See, the very simple layman example to understand. I have tossed a coin, it is in the air. Now you tell me when it is in the air, what is the state of the coin, whether it is 0 or 1. So I am more secure. Even the eavesdropper, he cannot make out whether it is 0 or 1.
Okay.
So this increases security also.
Okay.
So the best way I tell my students also, the best way to understand quantum computing is you imagine tossing of a coin. You have a coin in your hand. Here I know it is head or tail. I flip it. It goes into the air, flipping. On the top again, it will be in the head or tail position. In between, what states are there? That is what is quanta. That is what is the probability state. That is a quantum.
Yes, sir. The final question is, what is the future of quantum computing? Will it have a bright future ahead?
Naturally, it has a very bright future with few challenges that were coming. Last week, as I told you, all companies, they have started moving to QEC, quantum error correction techniques. They are developing new models are coming. So in this now we are into the second you can say generation of quantum computers, 2025. And I was told by one of the, I had a talk with the Bangalore company that they are developing their own quantum computer, and in 2025, yeah, Bangalore will get its quantum computer. So I told them, okay, whenever it comes, you give me a call. I will run towards your company's Bangalore, and I would like to see that. Because if you see the quantum computer, it looks like just like the chandelier light, which is at the center of your drawing room. It looks something like that. The only thing is that charges are there. Those charges have to be retained. The qubits are very fragile, because if they lose their charge, then everything information will be lost. So that is a very big challenge. They are very fragile. So people are developing, doing research, trying to get more better results, reducing the fragility and storing this. Because some companies, what they do, minus 273 degree Kelvin temperatures, they are keeping these qubits to preserve their states. Because once their state is lost, if you not do this, it will lapse, it will collapse to either 0 or 1, which is classical only. So we have to retain this in between state of that coin.
Yeah.
So that is important.
Thank you, sir. Next question. At present, at what stage quantum software education, development and usage are at present?
education, so what I found is that still it is in infancy.
Yeah.
Because now what I have seen in this month and in the last month, several seminars and webinars on quantum are being developed. They have increased in number. Earlier, if they were one or two, now you will get 10 or 20. So people are having FDP seminars, and I have attended many. There is IEEE, triple IT Delhi. There also we had on quantum. Atal also gave on quantum, that is AICT Atal program. That also I attended. I cleared the test and got the certificate from there. Then IEEE is there. Then many such quantum webinars are coming up. Conferences, seminars are coming up now. So by this, by the middle of this 2025, it will be on conferences. Will be on quantum only.
No, actually,
Thank
recently
you.
AICT has released the model syllabus for quantum computing along with CDAC just about a week back. AICT has
Yeah.
released the syllabus, UGC and
Yeah.
AICT jointly. They
Yes. Yes.
released the quantum computing syllabus for the
Yeah.
undergraduate along with
Delhi
CDAC.
University, Delhi University, they are teaching this subject in MCA, quantum
No,
computing.
no,
Even in BTech,
this will be adopted. This will be adopted by all the colleges once at
all the colleges
UGC
very
and
soon.
AICT.
Yeah, very soon. It is required. Actually, the challenge, a very big challenge is that the faculty is not that much trained, ma'am. I asked some of the faculties in my college also, my earlier college, former college. No, we have no idea on quantum. No, we don't know what it is. They are teaching digital electronics. Circuits they are teaching, and then no, we are not aware of quantum. And I have written a book on quantum. Okay, please give us one copy, then we will read from there. So faculty also wants now that they want to know about quantum. Some are scared. No, who will do? Already so many things are there. I have to do Java, I have to do C++, I have to do architecture. Why will I go with quantum again, new subject? So, but I found it very interesting when I was thinking about the coin problem. That actually attracted me to this. How is this possible? That the intermediate states also we are trying to represent with the help of direct notation in cat notation, the superposition states with the help of the probability distributions and all those. Okay.
Yes, sir.
I think Jairam
Final.
is wanting to. No, Jairam has been raising the hand for something.
Yes, sir. Only one last question, then I will put the direct question, sir. Job prospects of quantum computing.
Job, in fact, I am telling my HODs that I can teach quantum also. Why don't you float that subject also? So because in many universities, that subject is elective also. So if a teacher knows, he will say, I know that. So as far as job prospects are concerned, big companies, they need an expertise people. Those who have a lot of expertise, they need that. And students' point of view, basically students are important for teachers. And they hesitate. They will say, no, sir, we have to first give her a finish her PTech, then we will see if quantum is there, then we will do. So job prospects are not that much common that everyone will go and get the job, because they need a lot of expertise. They are themselves in the infancy stage. So how can they recruit so many people? Only they will take one or two people, creamy people, and then they will do. Every student or faculty they will not appoint. So job prospects will increase this year. That is for sure.
Mr. Jaykumar, sir, you can post your questions, sir, directly to him. Unmute yours and post your question. Mr. Jaykumar?
Unmute.
Sir? Unmute your mic and then you can. Yes, go on.
Sir, actually you have
Yeah.
told, good evening, sir. The session
Good
was
evening.
very nice. Sir, actually you had
Thank you.
told that while performing the testing of quantum programs, we need to, generally in classical one, we have, after writing the classical programs, we will do some type of, a developer will do unit testing. Then once it is done, it is transferred to the software is transferred to the testing team. There they
Yeah,
will go
development
for
team, testing team. Yeah.
there they will develop this functional testing, integration testing. Once it is done, then
Yes,
it will went
yes.
for. But what are the there we are having some testing frameworks, sir. Suppose if you take in Python means PyTest is there, which is used for doing unit testing. Similarly,
Mhm.
those type of testing frameworks are available for quantum for testing quantum
Computers.
program.
Yeah. Uh, See, some tradition, old tools, they have been used in such a way that, as I told you, reusability has to be done. Those previous classical tools, they have to
Hmm.
be modified or reused for these things. So some tools I have already mentioned, in between, like simulators are there. And even in QSkit, you can do some sort of testing also there. But, the directly, if I say, if for unit testing I have this tool, no, it is the tool that we had in classical computing that can be reused, keeping in mind that it is a quantum program now. So if it is a
Oh,
quantum program, there will be qubits, there will be qubit states, the circuit diagram will differ. As I told you that the initial state of the quantum register has to be given, then this initial state has to be correct. But the same thing is there. This is the sort of testing that we are doing. And some of the tools I have mentioned in the PPTs also, like they are developed and some are coming up, they are in development stage. I could
okay.
not find anyone for directly for unit testing like we used to have for classical ones, but classical ones can be adapted for quantums.
Okay.
That is what the literature says.
Okay. Okay.
Yeah.
The individual has to modify and then test it. There is no
Yeah.
definite, I mean, there are some
Yeah.
definite tools you have given already. So either you
Yeah.
can use them, or if you want, you can modify the classical system
Modify.
and
Yeah.
use it for
The
yourself.
test, the test cases and the test suits can be developed, but they will
Yeah,
change
okay.
accordingly. Like for
Okay.
example, correct input register was given or no? Yes, it was given. Then it was what was the output when this was given? So that way, truth table, your test table can be modified. Test case table.
Okay. Sir.
Yeah. Dr. Misra, so you can unmute and then ask your question, sir. Please unmute your mic.
Good
Yes.
evening,
Yes,
sir.
sir.
Good evening.
Sir, my question is that I generally teach the quantum mechanics like the harmonic oscillator, particle in a box, one-dimensional, hydrogen atom. So my question is that how these results are verified with the quantum computer, how we will link the results. Like the particle in a box in one-dimensional, we see the general formula of energy, n square pi square upon 2 ml, and wave
Mhm.
function is under root 2 by L sine n pi x by L. So, sir, how can we think about this? Quantum computer will give these results, sir.
Yeah, because quantum computers, that was it. Some initially also someone asked that so many states are being stored. If it is
Yes.
4 qubit, 2 is to 4 qubit states are being stored at the same time. So it can solve that problem. It will give you the results for that. That is not at all the problem because all the states available means all the qubits superposition states are available to us. And then it is finding best out of it because optimization is the main goal of our task. So optimized algorithms, optimize even in the agriculture field, even in your applied physics field, the molecules are moving, and the thing is that tunneling, quantum tunneling is also possible nowadays. Particles they cross that boundary also. Earlier it was not there, so they can solve that problem. That because that is the purpose of all these whatever complex problem is there, they are solving.
Sir, it means whatever the result we have right now in quantum mechanics, they are not verified by the quantum computer. They are only theoretical, but giving the results, classical
If we
results.
talk of physics,
Yes.
before quantum computers were there, it was only in physics lab only they were verified. but quantums, they are in process of verification. Some are verified also. Just as the hydrogen hydrogen atom. In an hydrogen atom, electron jumps to higher level. Planck's theory was there. So all these things hold. Schrodinger equation is also working. That shows the total energy.
Yes,
The
sir.
potential and kinetic energy. So yes, we are getting the results. That is not the problem at all. It will solve any complex problem.
Okay, thank you, sir. Sir, my last question is, you explained that we using an hydrogen atom or any atom, there are two states, ground and first. When
Yeah,
we provide the energy to the electron, it goes to the up, and when it comes to the
back to the
bottom,
state. Quanta
and
is
before,
released. Quanta energy is.
yes, sir, before reaching the ground state, there is the quantum computing. There is the whole story of the quantum computing between these two states,
Okay. Yes,
because
because when it is going, it is high excited state, then it is coming back. That time energy is released because quanta is an energy actually.
yes, sir. So, sir, how can we use, because you enhance that this point that the energy is coming to down, and we
Okay,
have to use this energy.
okay.
You told this, sir. Sir, can you
Yeah.
few words on this?
See, sir, if we have seen that the the light that travels, for example, photon, it is
Yes, sir.
as quanta. It's not continuous. Later on,
Yes, sir.
some other scientists they said no, it is wave like nature. Some are saying no, it is particle like nature. So the race was going on. So
Yes, sir.
yes. So the intermediate states we are trying to model. We are trying to find out with the help of these quantum model architectures, and then we are trying to give them in the circuits, and then trying to find out the outputs. So you want to say that energy, how this energy is being used?
Yes, sir. Yes, sir.
Because you see, E is h nu, we know that, and
Yes, sir.
this energy is released when an electron jumps back to its lower energy state.
Yes,
So
sir.
one is the higher state, excited state. One is the lower state. So they represent 0 and 1 only. But when it
Yes,
is
sir.
in between, when it is in between these two states, it is in superposition. So
Yes, sir.
superposition may we have naturally, like we used to draw anti-parallel spins in chemistry when we were in higher secondary school. One half
Yes,
arrow
sir.
up, one half arrow down. So
Yes,
that is the superposition state, and then we have to utilize that energy. Basically, we are using that energy to perform these different tasks. This is what the quantum energy is helping in.
yes, sir. Okay, thank you, sir.
Thank
Mm.
you, Dr. Mishra. So, Vishnu Surya, would you like to ask?
Yeah, ma'am.
Yeah,
I want
yeah.
to ask you.
Please go on. Please go on. The last one
Hi.
first.
Hi, sir. Good evening, sir. Myself,
Good evening.
Surya. I am pursuing my BTech. I
Mhm.
got a thought about storing the data of by getting the results from the quantum computing. You have mentioned that when the circuits lost the power, the data will be lost, right?
No, when you try to measure this, the state, superposition state of qubit, the superposition collapses. It becomes either 0 or 1, which
Yeah.
corresponds to the classical only. So the idea of quantum disappears.
Yeah. Yeah, sir. The data before will be getting lost.
Hmm.
We can convert into zeros and ones and store it, right?
No, actually, we don't know the state in between. You remember that coin problem? Just imagine that. We
Yeah,
don't
we
know.
we are.
How can I say, yeah, you are saying that we can store 0 or 1. We cannot store like this. No, we cannot store because we don't know the state. It's probability. It may be 0, it may be 1 when the coin is in the air. So
Yeah.
storing actually means like here, like what we can store is we can represent that particular superposition state by direct notation, and then we can find out for other qubits also for the entire system. We can find out what is the total qubit state. Then you cannot measure, nor you can replicate a qubit. There is a no cloning theorem you must have heard of in quantum computing. No cloning. It is theorem states that it is impossible to clone a qubit. You cannot clone a qubit.
Okay, sir. Thank you, sir.
Okay, welcome, sir. So thank you so much, sir. Mr. Mohan, sir, shall I go for the formal vote of thanks, or would you like to?
Yeah. No, it's okay. Go ahead.
Yeah.
Yes. Thank you, sir. Thank you for your wonderful Q&A session. Now I request our chair, Gomathy ma'am, to propose the formal vote of thanks.
Yeah, thank you, Dr. Killer. Good evening, all. I thank the organizing units CSI Chennai, IEEE CS Madras, and ACM Chennai for arranging this webinar today with the topic Quantum Software Development Lifecycle. We sincerely thank Dr. Rajiv Chopra, Associate Professor, CSC, Gurudai, Bahadur Institute of Technology, Guru Gobind Singh, Indraprastha University, Delhi, and the author of the book, Quantum Computing Techniques, Theory and Practice, for his informative session. Dr. Rajiv highlighted in his presentation today on the novelty of QSDLC compared to classical SDLC, the application of QML, quantum machine learning, quantum deep learning, and especially the challenges in quantum computing at every stage of quantum software development lifecycle. He discussed how we can still reuse the techniques of SDLC in QSDLC. He also highlighted how the quantum programming languages differ from the classical one, and he guided how to reuse the codes in QC. He narrated QSDLC in detail, which comprises the various stages such as quantum software requirement, quantum hardware requirement, quantum software requirement analysis, quantum software design, quantum software implementation, quantum software testing, software deployment, software maintenance, and quantum software reuse. He deliberated very, very in detail all these stages of QSLDC. And Dr. Rajiv compared the difference between quantum simulator and the quantum emulator. He also guided how to install IBM QSKit package to experiment some of the QC algorithms. Finally, he concluded that when QC is able to compute any task in 5 minutes, which will take 10 to the power of 25 years by a supercomputer. I thank once again Dr. Rajiv Chopra for answering the questions raised by the participants. I sincerely thank our mentor, Mr. H.R. Mohan, Chair Events, IEEE CS Madras, who worked meticulously to bring speakers for introducing the trends in computer technology for the benefit of our members. I'm thankful to the participants who joined in live Google Meet and YouTube live streaming. I thank the event team members from the organizing units for their support in arranging this event. With these warm words, we move to the end of today's event. Thank you all and good night.
Rajiv, can you just show the book so that we want to capture the screen?
Yeah, one snapshot.
Yeah. No, just you can move it. No, you can move it to your
Left or right?
left or right. Yeah.
Yes.
Sir, is this
hold on? Yeah, hold on.
Raju, sir?
Yeah.
Is this book available in Amazon or?
Yes, it is there on Amazon. It is there on Flipkart.
Okay, sir. Okay, sir.
Yeah, it is there. Yeah.
Okay, thank you, sir.
Yes.
Thank you.
Yeah.
Especially in image processing.
Quantum annealing. Yeah. Quantum annealing is basically working on, the principle of, like, for example, we are trying to find the possible solution is the lower energy state, the lowest energy state. So annealing or this problem happens when quantum coherence is measured in quantum transportation. I think in image processing, I've not applied on image processing. I'm working on quantum image processing. Not actually implemented, so I've not seen.
Sir, your PowerPoint is given a lot of reference materials, right? No, sir.
Yeah, you
Yes,
will
yeah.
get there.
Yeah. So the research groups working on different applications or something. If we are able to get it, then I think we can refer to those sites and talk to them and get more details. Yeah. Thank you so much.
Yeah.
Mohan, sir?
Yeah,
Shall we-
thank you. Thank you, Dr. Rajiv. So wonderful
Yeah.
session, and it coincides with the International Year of Quantum Computing. So yours is the first lecture for us. The
Yeah.
International Year of Quantum Computing. So 2025, now it is being celebrated the whole year.
So one small request from my end.
Yeah, please go on.
Actually, it is good. This overall, Raju sir has shared the overview of quantum QSDLC, but it is better if you can, in future, if you can give similar, based on topics, presentation is very good for
Yeah, that's what we
individual.
can have. FTP, that's what he said. FTP, you can arrange an FTP to have at least a week, 5 days or something, and you can touch upon how to really experiment. I think you want to probe into the experimentation, right?
Yes, madam. Actually, I am the learning. I am a Qiskit learner, madam.
Okay, that's what. So you can
and
have
even-
you can just find the experts in the in this field, and you can conduct a tutorial section.
Yes, madam.
So that you can go one level deep.
Yes, madam.
This is only an overview. We want to bring it to the members that such things are happening in the world.
Yes.
So further exploring and finding the depth of it, we have to see.
Yes, madam.
Okay.
So you can visit the IBM site, which has got excellent tutorials.
That's what he has
and
given in the reference
material. Yeah, IBM site has got many reference material.
Okay.
Okay, sir. Yeah, then it is. Thank you, Dr.
Thank
Rajiv.
you. Thank you, Dr. Rajiv.
Thank you, ma'am. Thank you.
Yeah, good
Okay.
night, sir.
Thank you.
Good night, sir.
Thank you, sir. Thank you, madam.
Yeah, sir.
Thank
Thank you all the participants.